Good. Okay.
Perfecto, vamos a esperar unos minutitos, Isabel, y la presento a nuestros alumnos.
Yes. For me, I don't think you will need to translate. I understand Spanish well. I can speak most, but not give a lecture, a full lecture in Spanish. Hablo español, pero dar toda una charla en español para mí, con biología molecular y todo, es muy difícil. Yeah, I don't think it's necessary, but thank you very much anyway.
Perfecto, perfecto. Muy bien, le comento a nuestros alumnos que tenemos traducción. Ustedes pueden escuchar a la doctora si quieren en inglés o pueden elegir en la sección de traducción escucharlo en español, ¿sí? Tenemos abajo, aquí ven mi pantalla, para que ustedes puedan elegir en el idioma que quieren escucharla a la doctora. Nos ha dicho que ella entiende bien español, así que ya vamos a ver entonces en la sección de preguntas y respuestas cómo se siente más cómoda en manejarse. Bien. Me pregunta Nico y te pregunto a vos, ¿la grabación va a ser en ambos idiomas o la grabación va a ser en español? ¿Cómo se graba?
La verdad que no lo sé, Dolo.
Veremos cómo se grabe, calculamos que en español.
Calculo que se va a grabar los dos audios y vamos a tener el video con el audio original y el audio en español, digamos, traducido.
Perfecto, perfecto, perfecto. La idea es comenzar puntuales, así que vamos a esperar 1 o 2 minutitos más para que ingresen los alumnos. A veces el Zoom hace que entren despacito y vamos a darle unos minutitos para que ingresen y tenemos una hermosa, hermosa clase con la doctora Chats, así que vamos a esperar unos minutitos más, así todos pueden disfrutarla.
Dolo, acordate de
Sí.
avisarme cuando empiezo a grabar.
Perfecto. Les comentamos también que esta semana hemos ya abierto el aula virtual. A cada uno de los alumnos inscriptos tiene que llegarle su usuario y contraseña. Si no les ha llegado, les pido que revisen el correo no deseado, porque lamentablemente a veces cae allí en el correo no deseado. Y si no está allí tampoco, les pido que nos escriban a cancerherenciaroffo@gmail.com para que podamos hacerle llegar el usuario y contraseña. Ahí lo que vamos a tener subidos son los videos de cada clase. Lamentablemente por una cuestión técnica la clase anterior no fue grabada, pero ya de aquí en más van a tener todas las clases allí. Y también vamos a empezar a subir un poquito de bibliografía. Tenemos ya, con la autorización de la Sociedad Española de Oncología, el libro de cáncer hereditario de la Sociedad Española, que es un precioso libro muy actualizado de 2019, así como empezar a leer un poquito para aprender y disfrutar más de estas clases. Bien, ya siendo 16:03, vamos a dejarle compartir a la doctora su pantalla. Vamos a recibir, Nico, si querés empezar a grabar. Vamos a presentar a la doctora Achat. Ella es médica genetista, doctora en oncología. Actualmente se desempeña en el Hospital Sirio-Libanés de San Pablo, Brasil, donde es coordinadora de la unidad de oncogenética. Es un placer tenerla a Isabel con nosotros. Isabel, si querés compartir pantalla, ya te dejamos.
Muy bien. Muchas gracias por la invitación. Es un gran placer de estar acá hoy, pero voy a continuar en español, en inglés, perdón. So, good evening, everybody. Can you hear me well?
Sí.
Good. Wonderful. So today I'll be talking to you about germline testing in hereditary cancer. And first of all, there is a concept that most of you are probably aware, but it's always important to remember that cancer is always a genetic disease. We know that a cancer is some alteration, some initial mutation that will occur in a normal cell, for example, a breast cell, and this alteration will be followed by several other mutations that will continue to grow in the cell. And as the cell divides, it will eventually lose the capacity to know when to stop dividing. So cancer is genetic, that we know already. But there are two concepts that are extremely important, and we have to remember every time we think about genetics in general. So cancer is genetic. I was meaning a somatic alteration. What does that mean? These are alterations that will happen throughout life, for example. As a person gets older, we know that their cells will continue to accumulate alterations, but also a good example of somatic alterations, that is, in the DNA specific to that place, is, for instance, sun exposure. We know that someone who exposes the skin to UV will be eventually be accumulating damage in the DNA of those cells. Tobacco exposure, for instance, is also something that will be accumulating, as well as radiation in general. But here today, we will be talking not about these somatic alterations or about the genetic aspect in general of cancer. We'll be talking about germline alterations, germline variants or mutations. These are innate. People are already born with it. I'm talking about a cell that will be receiving a sperm that will enter and will have the generation of an entire being, 2 cells, 100 cells, and a whole embryo. And this embryo will be carrying the exact same alteration that was present when there was the fecundation. So here we have a clear example of heredity. So here the father and the mother got married. She already had breast cancer at the age of 43 and a second cancer at the age of 54. And they had 2 children, 2 women who, in the case, my patient was this lady who came to me when she was 59 years old. And when she came to my office, the main question she was bearing was, what can I do to my children? because I've already had three cancers. Is there any way I can detect if my children are at a higher risk for developing cancer? Can I know if I have something in my genes that have enhanced my risk for developing a cancer? And the third question was, I have a metastasis now that was recently diagnosed in my lung, in my brains. Should I do any kind of different treatment? Is there anything new that is related to genetics or heredity that can help me with that? So, this is a very typical case. We have over two generations of people who were attained by cancer, not only breast, ovarian cancers, but also other tumors such as pancreatic, prostate cancer, and even lymphomas. And this is a typical scenario of a hereditary breast and ovarian cancer family. So, what did we do with that lady? We collected some blood, but it could be also the saliva, because I'm not interested in testing her tumors. I'm interested in getting to know what is her DNA, her constitutional DNA, the DNA she inherited from dad and mom. And we found a germline variant in the BRCA1 gene, which was a change of a C to a T in the position 1687, leading to a glycine stop change at this position, at this codon 563. This is a very typical situation where we know that the person has an alteration in the BRCA gene, one of the main tumor suppressor genes, and that leads this person to stop producing adequately this variant, this protein. And what do we know when we have a lack of production, for instance, in the BRCA1 gene or in the BRCA2 gene? First of all, everybody thinks about breast cancers. The numbers, they will eventually change from one study to the other, but the risk of developing a breast cancer in those who have a deficient production of BRCA gene will be around 70 to 80% lifetime risk of developing a breast cancer, and a high risk of developing a second primary breast cancer that will be in the range of 20 to 30, 40%. Also, there is a high risk of ovarian cancer, prostate cancer, pancreatic cancer, and other cancers as well. So, what should we do when we have those high risks and we find a germline mutation? We can do early screening and we can do several other things, and we'll be talking about this here today. One of the concepts we have to know, especially when we're talking about South American populations in general, but Central and South American mostly, the major part of studies performed until now are in Caucasian populations. We do have some Latino studies in the United States, but in Brazil, for instance, there was very little information in the landscape of BRCA1 and BRCA2 germline variants, pathogenic variants in our population. So this was one study that we performed in several centers, different centers around Brazil, and we were able to gather 449 individuals with either a germline mutation in BRCA1 and BRCA2. And we found actually what we expected to find, which is several germline mutations that have never been reported elsewhere, 26 novel variants that were pathogenic. What does that mean? That we are different from the rest of the world. Each population, each distinct population is different. Colombians, well, okay, they are Latinos, but they have their own characteristics. So this is just to stimulate you all, if you're in the clinic, to think about research every time you are in front of one of those individuals who carry germline mutations. And if you cannot do research alone, it is important to be in contact with other centers that are currently studying. So we are not stopping in BRCA1 and BRCA2. These were the most studied and the more common germline variants found in hereditary breast cancer syndrome families. But we do have several other genes that are known to be part of this. We expect BRCA1 to be and BRCA2 to be 50% of all the alterations. But what we know now, and we have been studying since 1990s, we have three major types of genes involved in cancer risk. We have high penetrance genes, which confer a very high lifetime risk for developing a cancer. So here we have BRCA1, TP53, CDH1 that predisposes to breast cancer, but also to diffuse gastric cancers. But also we have other genes that are considered high penetrance genes, such as STK11 and PALB2. STK11 is related to Peutz-Jeghers syndrome, and PALB2 to breast cancer mainly in those individuals. This was what we call the first wave. These were the first genes to be identified, and they were very typical. And what's good about them? It's because we know them well, and we know how to follow individuals who have these genes altered. We know how to stop those individuals just by following them. And if we know when to start screening, we may change all the story, the natural history of cancer in those families. So it is of great clinical utility, and we have a very impactful cancer control in those individuals. So, what was the second wave? The second wave came with moderate penetrance genes. PALB2 was considered to be moderate, but has recently been upgraded as a high penetrance. But ATM, CHEK2, BRIP1, RAD51C, RAD51D, and others, they are genes mostly related to breast cancer and ovarian cancer, and individuals who are at risk, and also prostate cancer, mainly ATM and others. But those who are carriers of germline variants in those genes, they are at a moderate risk for developing cancer. We're talking about 30, 40%, even 50%. These situations are very challenging. These were genes that were discovered in the late 19s, in the early 20s to 2000. And what we know until now is not enough to define clearly what is the very correct follow-up. We have some indications on how to follow them, but it is not entirely clear on how to proceed, for instance, with prophylactic surgeries. In most of the cases, there is no clear indication of any kind of prophylactic surgeries in individuals with moderate penetrance genes. And we were expecting for a third wave, which would be other genes that would explain all those individuals who have typical family histories, and we never get to understand what is the alteration that is causing such a high risk in those individuals. But instead of that, we never found another third wave. We never found other high penetrance genes. What we did find were a series of low penetrance genes. And for that, this is a paper that was published last year in Nature Reviews. And here we have a very clear way of describing those three waves. The first wave, high risk and rare alleles, they're not very common in the general population. Rare and moderate risk alleles that are present in some individuals of the population. But again, they confirm they're still rare, and they confirm moderate risk. And here is a big number of low penetrance genes. Alone, these genes and alterations in these genes, they do no harm. But the issue is that combined, if we get 80, 100 genes like these, and we are able to combine them, as well as with personal habits such as obesity, alcohol. We know that these will enhance the risk, and they will greatly enhance the risk for cancer, for instance. And there is a mathematical calculation nowadays, and I'll try to explain to you a bit later what are the polygenic risk scores that will bring us information about these low penetrance genes.